Hello and welcome to our presentation on the construction estimation of the Shamaran Mall. This is a student project at Ryerson University and is for educational purposes only. My name is Dana and I am a part of the project management team here at Savvy Construction. Today I will give you an overview of the project and what decisions and assumptions we made. I will take you through our construction sequence as well as what resources we plan to use in the project. And lastly, I will introduce you to our work breakdown structure. Here is a plan view of the site. Our working area is hatched in pink and it is to be the future Shamaran Mall. We have identified our laydown area in blue hatching for site trailers and equipment and material storage. We have two access and egress routes to and from the site which allow for the connection between two different roads. When analyzing this project, there were a few issues which required further care. This includes one overall goal and two subsequent goals. First goal can be simply described as the epitome of construction, the three pillars of project management. This is to ensure that there is an adequate balance between project cost, duration, and scope to maintain the quality. This is paramount in ensuring that the project is a success for every party involved. The first consideration included selecting the appropriate dump sites for the disposed soil while considering the relationship between the dump site and vulnerable water sources. This also involves selecting the correct route to the chosen dump site or sites. The options for dump sites were 1, 2, and 3. Dump site 1 was the closest to the site, dump site 3 was the farthest, and dump site 2 was somewhere in between. The catch was that dump site 1 was located very close to potable water and below the water table. Dump site 2 was a kilometer from the closest water surface body and above the water table and located in an area of potable water. Dump site 3 was a kilometer from the closest surface water body, above the groundwater table, and not located in an area of potable water. The route options were Route A and the toll highway. Route A poses certain speed restrictions and time restrictions regarding how many trucks may be on the road during what times, and the tollway imposes no restrictions, but there is a fee associated with its use. Another issue included selecting which equipment to use and how many of each type so that an adequate balance between a minimal cost and duration was obtained while still maintaining the quality of the project. So this included selecting the graders, hauling trucks, packers, excavators, loaders, and dozers. We were faced with the option to buy additional equipment, and some equipment types had multiple models to choose from. This shall be discussed in further detail in the cost estimate section. To solve these problems, a linear combination was performed with the objective of minimizing the total project cost. The decision variables were the number of trucks of each type on each road. The constraints included that Road A could only have 10 trucks on it in the morning, and the number of trucks must be a positive integer, the total number of trucks must be greater than 0, and that the hauling operations should be completed within a year. This was an arbitrary decision made based on the goals of the team. And you may have noticed that only dump sites number 1 and number 3 were considered on the slide. And this is because dump site number 1, as you may remember, is in an area vulnerable to contamination of the water. So it was decided to dump all non-contaminated soil at dump site number 1 to preserve costs, and all contaminated soil at dump site number 3 as it is not vulnerable. Next, I will take you through the construction sequencing. We have identified 4 major construction phases. The first phase, shown here, is titled the pre-construction activities. These activities are defined as the works that commence prior to excavation. So this includes geotechnical investigation, construction of the site access and egress, site delineation with fencing, and exposing of utilities. The second major category is the removals and demolitions works. This includes site clearing to remove vegetation and the excavation of the soil. The third major category is the earthworks. This is a large portion of the project. It includes surface preparation for the foundation works, placing and compaction of the fill, fine grading the soil for the construction of the basement level, and quality control measures. The final category includes the foundations works and involves erecting the formwork, installing the rebar, pouring and curing the concrete, stripping the formwork, and quality control measures. Next, I will take you through our work breakdown structure, or WBS. The WBS for this project is separated into 2 categories, the indirects and the directs. This is in order to consider all types of project costs. The indirects are separated into the staff, office supplies, securement of funds, purchase of company vehicles, and the purchase of construction equipment. The staff includes administrative, janitorial, and security staff. The office supplies considers the purchase of office trailers, equipment, and amenities. The securement of funds considers insurance and bonds. The purchase of company vehicles includes 5 cars per operations staff and a pickup truck for each foreman. The construction equipment purchased is described in the following section. The directs follow a similar format to the construction sequencing described previously. The buckets include the pre-construction activities, removals and demolitions, hauling, foundations, earthworks, and site services. Site services include tasks that are ongoing throughout the entire duration of the project. So these include surveying, site sweeping, water truck rental, site cleanup efforts, and traffic management. Here is a better look at the earthworks and site services.
Hello, my name is Elias and I'm the cost estimator on the team, and I will discuss the risk analysis and equipment cost estimation for this project. A risk analysis was performed to gauge the probability and impact of various hazards and dangers that may arise during the course of the project phase. A risk identification was first conducted, covering risks regarding equipment, soil disposal, the environment, worker and public safety, and on-site hazards. Some risks in this project were shared between Savvy Constructions and the applicable subcontractors that shall work on site. A qualitative risk assessment matrix was created for the analysis. A score was calculated for each risk in order to quickly identify the critical and major risks. Finally, mitigation measures and solutions for each risk activity was proposed in order to decrease the severity of the impacts. The risk scoring system used was based on the probability of the risk activity measured from 1 to 5, 1 being very low and 5 being very high probability. And for the impact, the range was also 1 to 5, 1 being very low and 5 being very high impact. By multiplying the probability and the impact of the associated activities, the scores provided then translated to indications of minor to critical outcomes. The next 3 slides show the risk activities identified for the project phase, their causes, their respective owners, scores, and the appropriate mitigation measures to employ. The following risk activities from this analysis shown here are the activities that required the most attention and had an effect on the team's decision-making process. For example, in deciding whether to dump soil at dump site number 1, the risks of contaminating the potable water nearby was critical. Therefore, it was decided to only dump non-contaminated soil at this site. For a major risk, such as inadequate lagged shoring operations, which could cause soil to collapse on company and subcontractor workers, ensuring that the soil conditions are sufficient when shoring is installed, and having shoring components, including struts, rakers, and tiebacks, adequately placed for bracing, can help in terms of avoiding unwanted consequences in the event that the activity is conducted below the company's standard. For the equipment cost estimation, the following general parameters were applied to each cost estimate, which includes the fuel cost, efficiency, capacity of the equipment, status of the equipment, meaning purchased, owned, or rented, energy consumption, and operator wage. For the truck cost estimation of dump site number 1, the volume of contaminated soil was considered, while for dump site number 3, the non-contaminated soil volume was considered. Key parameters include road and highway distances, travel time per trip, the maximum trips a truck can take within a day, the volume dumped per day, and toll price when applicable. The estimation found that the cost to transport to dump site number 1 will be $193,457,117 in a single year. And for dump site number 3, the cost will be $17,904,681 for 6 months transport time. For each of the remaining equipment items, productivities were calculated to ultimately find the costs. Starting with...
Hi everyone, my name is Mohammed Dalati, the infrastructure engineer for Savvy Construction. Today I'll be discussing the summary of qualifications for the cut quantities. As seen in the figure, the soil is classified as rocky, shown on the left side, and soft, shown on the right side. rocky soil is subcontracted, whereas the soft soil is self-performed. Next slide, we'll talk about the excavation stage. The excavation stage is divided into 3 phases: rocky, soft, and contaminated soil. Phase 1 includes a rough estimation of the excavated material done by the subcontractor. This allows us to know the amount of soil to be transported. Phase 2, a thorough calculation of excavated material to determine the amount of soil to be reused and transported. Phase 3, contaminated soil exists 1.8 meter below the surface throughout the construction site. Savvy Construction will be responsible to provide contaminated free soil. For Phase 1, the figure on the left side shows the division of rocky soil regions, whereas the figure on the right shows the contour lines and elevations extracted. The final ground elevation was set to be 1285.3 meters, and volume was obtained per division based on the following equations shown. After doing the math, approximately 1.6 million of rocky soil shall be transported. In regards to Phase 2, it followed a more sophisticated approach, and soil regions were divided into each grid line. The findings were reported as approximately 270,000 of soft soil needs to be reused and/or transported to suitable dump sites. Lastly, and for Phase 3, contaminated soil, and according to the Ministry of Environment, there is a threshold of what is considered as a safe concentration beyond which soil should be extracted. That is 220 milligram of barium per kilogram of soil, 36 of boron, and 120 for lead. This table summarizes the regions covered and whether the soil needs excavation or not. In conclusion, approximately 87,000 cubic meter of soil was considered unsafe and needs to be excavated. Thanks for your attention, and from here, Jad will take over.
Hello, my name is Chad. I'm the geotechnical consultant in Savvy Construction, and I will be walking you through the filling estimation for Sherham Mall. The filling process is divided into 2 phases. Phase 1 is filling the contaminated regions that were previously excavated with soft, safe soil. This plan view shows the regions that need to be refilled with safe soil. They accumulate to a total of 87,330 meter cube. Half of this quantity will be safe soil that was previously excavated, soft soil, and the other half will be replaced with soil imported from nearby quarry. Now moving on to Phase 2, which is filling on top of the foundations. After the foundations have been poured, Phase 2 initiates. 1.7 meter of soil will be placed on top of the foundations. As you can see on this slide, the left picture shows the cross-section of the foundations to be filled. The area is composed of 2 rectangles. The picture on the right is the top view of the foundations. Only the regions highlighted in this plan view are to be filled with soil as instructed by the owner. A total of 15,204 meter cube will be needed to fill the foundations. As we did in Phase 1, half of that amount will be from previously excavated safe soil, and the other half will be imported from nearby quarry. To summarize everything, the table on the top shows the volume of safe soil that needs to replace the contaminated soil on site. The table below it shows the amount of soil that needs to be finished on top of the foundations. Therefore, we need a total of 102,534 meter cube of soil, out of which 56,883 will be from excavated soil already available on site, and another 56,883 will be imported soil from nearby quarry.